Swayam Prabha. Digital India. Educated India.
Good morning. Last few lectures we have been looking at the displacement method, and in the last lecture I told you that I have done as much as I can do to explain the different nuances in application of the displacement method. In this particular lecture I am going to end my discourse on the displacement method by actually taking you through the last few points that I would like to make in terms of the lecture. Okay? And that essentially boils down to how to treat. See, support settlement and support flexibility are not issues in the displacement method, because when you have support displacement and support flexibility, all it does is that it introduces another degree of freedom and it has absolutely nothing to do. So remember, what we had talked about was the various things. One was member loading, other was support settlement, support flexibility, and then we had lack of fit. Lack of fit was specifically in terms of trusses, and since I have not yet dealt with truss, I shall do that in this particular lecture. The only other thing, if you remember, was temperature related effects. Okay? And here I am going to today start off by talking about temperature effects in displacement method. Okay? Now, what is the temperature effect? If you remember that if you are looking at a beam frame, we are only considering flexure, then we only consider the differential temperature. And the differential temperature, if you look at it, if you have a cross section which is, this is the top, this is the bottom, and this is your depth, then okay, and this is your, let's say, neutral axis, then essentially what you are interested in is this variation. At the neutral axis, temperature is 0, the temperature difference. This is delta T, by the way, so it's not as if at the center you have freezing. It's just that there is no rise of temperature at the neutral axis. Here you have delta T at the top, you have delta T at the bottom. Obviously, for it to be 0, this is only the differential part. In reality, you might have two parts to it. I am only looking at the differential part because that's the one that causes flexure. And if you remember, I had actually gone and computed earlier that the curvature in the cross section due to delta T is given by alpha delta T top, delta T bottom upon delta T top upon 2D, where D is the depth of the cross section at that particular point. Okay. So this is the curvature. Now the question is that, remember that temperature is a member effect. So member effect, the only thing the member effect is brought in is through the fixed end moments. Okay, so the point to note here is that if you look at it, if you look at the member force and member deformation, it essentially is what? If you look at it, MAB is equal to 4EI upon L, theta AB. Now this theta AB is due to displacements, okay? Plus 2EI upon L, theta BA, again theta BA is due to displacements, okay? Plus fixed end moment at AB. So the member effect, the member load effect is only incorporated in the displacement method by introducing the concept of the fixed end moment. And the fixed end moment is one in which theta AB and theta BA are put equal to 0, and you find out the member end moments due to the load only. Okay? Now here there is no load, there is a temperature. However, it's again a member effect. Remember I talked about that member effects are what? Member effect is lack of fit, temperature, member load. All these are effects at the member level. And the displacement method, member level effects are only incorporated in finding out the fixed end forces. In this particular case, since we are looking at flexure, the fixed end forces are the fixed end moments. Okay? So ultimately, what if we can find out the fixed end moment due to a particular temperature profile, we have solved the problem. Okay? Now let us take, I'm going to solve it for the simple case. Now this is the curvature induced due to. So how do I find out the fixed end moments? If you remember that the way we found out the fixed end moments was by, we're going back to first principles. We found out the rotations we found out the member and rotations due to the member effect. Okay? Now what is the member effect? A temperature. Okay? How do I compute these? Well, how did I compute these? Okay? Remember that using the virtual force, theta AB is equal to 0 to L M1 into curvature dx. Theta BA is equal to 0 to L M2 into curvature dx. What is M1? M1 is the bending moment in the member due to a unit virtual force corresponding to theta AB. So that gives me the virtual displacement this is my M1 diagram, and M2 corresponding to theta BA, and so M2 turns out to be this is my M2 diagram. So for the temperature effect, we can find out theta AB and theta B. I have already solved this earlier, but I'm just going through the steps again just to refresh it. And therefore, see, now I'm going to assume the situation that everywhere along the length of the member, the top fiber sees delta T top, and the bottom everywhere sees delta B bottom. In other words, the temperature gradient is uniform along the entire length. If I take, so I'm actually solving it for a specific case where I have uniform temperature gradient across the cross section over the entire length. In that particular case, beta turns out to be a constant given by this. Okay? So once that is done, so this is a constant, so I just need to integrate m1 dx, and so therefore I get theta AB is equal to area under the curve L by 2, so it's going to be alpha L delta T bottom minus delta T top upon d. Now this theta AB, you will see that M1 is just the opposite of this, because this is the curvature to get positive curvature this way. Okay, so this is negative, so I'm going to get theta AB is equal to negative. Okay, and theta BA turns out to be equal, alpha upon 4D. Okay, theta BA is minus alpha L plus, because this is the same as that, and therefore these are my theta AB. And how do I get the fixed end moments from this particular equations? Well, remember, how did we get the fixed end moment? Well, we had to apply the moment which would give me just the opposite of these theta AB, so that the sum total of them gave me 0, so that I could get my fixed end moments. So without much ado, I'm going to go into computation of the fixed end moments. And so therefore, what are they? Remember this, that fixed end moment is going to be AB is going to be equal to 4EI by L into alpha L minus here delta B minus delta T plus 2EI by L alpha L okay. So this is equal to minus 4EI alpha plus 2EI alpha. This is going to be equal to minus 2EI alpha into delta TB delta T upon 4T. Okay, so this will be equal to EI alpha delta TB delta T upon 2D. Let us look, that is my fixed end moment at AB. Let me look if I am dimensionally consistent. What are the units of alpha? Alpha into delta T is going to be meter into meter, meter by meter, meter by meter. Okay, so meter by meter is essentially dimensionless. What are the units of E? Newton per meter squared. So Newton per meter squared, Newton per meter squared into, this is meter fourth. So this is going to be equal to Newton per meter squared into meter fourth is going to be equal to Newton meter squared. Newton meter squared divided by D, which is meter, is going to become Newton meter, and that is fixed end moments. So the units are consistent. So this is the unit, I'm sorry, this is a minus here. Okay, so this is the fixed end moment at AB, and similarly you can actually get that the fixed end moment at BA is going to be equal to EI alpha delta bottom delta top on 2D. And so therefore, if I have a uniform temperature gradient, so the gradient is uniform temperature gradient, then, and with the bottom being hotter than the top. Okay, so in other words, it expands in this way so that you get it to be equal to the opposite. Okay, now I'd just like to make a point here, and that is, remember that theta AB is equal to minus and theta BA is equal to plus. So therefore, when we substitute in here, this has to be plus and this has to be minus, and therefore this becomes plus and this becomes plus. It is, remember that the rotation that we get is this plus this rotation has to be equal to 0. So therefore, when this is minus, this plus this is going to give you 0. Then this plus this is going to give you 0. Okay? So therefore, the fixed end moment here has to be positive, and similarly, the fixed end moment at this has to be negative. And so if we show it for uniform temperature gradient where delta B is greater than delta T. In fact, temperature differential at the bottom is greater than the temperature differential at the top. Then we have, and it's uniform across the entire length, then we get fixed end moment AB and fixed end moment at BA equal to, I'll just write it down. I've got BA over there. AB is equal to note that these two fixed end moments that I have written down over here are essentially for where the increase in temperature at the bottom is more than the increase of temperature at the top. Okay, mostly it would be increase of temperature in the bottom and decrease of temperature in the top, because you have to have neutral axis 0 for pure flexure. Okay, and also the fact that it is uniform over the entire length. In other words, the top fiber across the length sees delta T bottom, okay, delta T top, and that's a negative temperature, and delta T bottom is uniform across the length, and that's a positive temperature, to get the directions that you have. Of course, if delta B and delta T turn out to be different, you'll get them to be minus. Okay, so this gives you the expression. Now, if there is a different temperature variation, in other words, you have different variations of temperature across the lengths, then of course you will not get these two, you will get some other. But the fact is that you should be by now totally certain about how to evaluate this effect. Once we have the fixed end moments, there is no difference between the member end, loads or member temperature. Okay, excepting that once you got the member end moments in temperature, you do not have a bending moment due to the additional bending moment in the member due to the temperature effect as you do for the load. Okay, in other words, the simply supported beam subject to temperature has 0 moments, whereas a simply supported beam subjected to a load will always have a bending moment diagram associated with it, which has to be superposed on. In the temperature, you don't have the superposition. Otherwise, once you've calculated the fixed end moments, you use the same principle that we have already done earlier. There is no difference when you have to consider the temperature effect. Okay, so we have now done with considering the temperature effect and how to incorporate it into the displacement method. I am now going to move on to how to use, in other words, I'm going to look at the displacement method for a truss. Okay, how do we apply the displacement method? Because the reason why I'm looking at this, the displacement method is exactly the same, excepting for the fact that in a flexural member, the member end force deformation relationship essentially related the moments with the rotations. In this particular case, the force deformation relationship in a truss, it only has axial forces and axial deformations. So the member end force deformation relationship should essentially relate the axial force and the deformation in the member. Okay, so let us look at how to tackle that. This is my truss. Okay, now I'm going to consider it to be fixed over here. Okay, just like I considered the simply supported, which was the simplest statically determinate flexural member, I'm going to consider the simplest statically determinate axial member, truss member. So here I have load F, and due to this I have a displacement which is U. Okay, so since this is member I, I'll call this force I and member I. How do I determine this relationship? Well, I know that Ui is equal to Fi Li upon Eai. This is assuming that Ea is a constant and only the load is applied at the member end. I know this. This I've already evaluated earlier. So that means my force deformation relationship will be Fi is equal to EAI upon Li into Ui. And this is my member end force, this is my member end displacement, and this is, look at this fact, the difference between the member end for flexure. In flexure, you have two rotations and two moments to define the member end forces. For the truss, you only have single force, single displacement. Okay, and this is the force deformation relationship for a member. Now, if you happen to have, by and large in trusses, you do not have forces acting in the center. Okay, you normally always have member end moments, and that is the reason why the force deformation relationship is essentially this for a member. So I can write it as F is equal to EA by L into U. Note, what was it for a flexure? It was MAB is equal to 4EI upon L theta AB plus 2EI by L theta BA. Of course, in a flexural member, you may have member loads, and that's why you have the fixed end moments, etc. Okay, in this case, you normally don't have that, and therefore you do not have this aspect. Of course, you might have a temperature problem, and therefore this can be written generally as F is equal to EA by LU plus fixed end force. Which is the fixed end force? This is the force developed here due to a member effect. Okay, we'll see that later. Okay. So let's look at this. Moment. Look, EI by L, EI by L, EI by L is Newton meter. Okay, so the units here, Newton meter, it's moment per unit rotation. So these are units are Newton meter per radian, and it's like a torsional coefficient, torsional stiffness constant. Okay, here EA by L, if you look at it, is EA by L is Newton per meter. Newton per meter is something like a stiffness constant, spring constant. Okay, so this is similar to that. It's force per unit displacement. Okay. So once we have this, how do we tackle a particular problem? And let me take a specific problem here and see how to solve it. I'll take a simple problem here because you can actually take it for any kind of thing. I just want to reduce the number of degrees of freedom, and that is why I'm considering this effect. Okay, the reason behind why I have chosen this is in the displacement method, what do you start off with? You start off with defining the degrees of freedom. So this is essentially all truss members. Okay, although this does not look like a truss that you would have normally, the reason why I'm taking this is because it is simple. I'll take up another thing also in which we will see how it works. Okay, so here if you look at it, this is a statically indeterminate truss. Okay, you cannot find out the forces in each of the members given this load. Okay, so how do you use the displacement method? Let's go through the steps. First, determine degrees of freedom. How many? I have A, B, C and D. So I have remember that when you have a truss member, how many degrees of freedom per? You do not have the rotation, so you only have two displacements. So the unconstrained degrees of freedom are 2 into 4 So 8. And how many constraints? You will see that 1, 2, 3, each one has 2 constraints. So constraints are equal to 6. So there are 2 degrees of freedom. What are those 2 degrees of freedom? I'll define them as R1, R2. Note that I always define my displacements along the positive. This is my coordinate system for the structure. So my degrees of freedom are positive in the positive direction. So R1 and R2, these are my degrees. So to determine degrees of freedom, define degrees of freedom. We've done it. R1 and R2. R1, horizontal deflection of D, vertical deflection of D. So we define that. Next, what is it? The third step is defining the member and force deformation relationship. So how many members do I have? I have AD, I have BD, and I have CD. For AD, what is the member and deformation relationship? It's going to be FAD is equal to EA upon L. L you will see is equal to 5, so EA upon 5 into UAD. Then FBD is equal to EA by 3 into UBD. FCD is equal to EA by 5 UCD. Simple relationships, but we've written the member and force deformation relationships. Okay, what's the next step? See, I'm actually going through the displacement method as I have defined it. The next step is the kinematics. So what do I need to do? In terms of R1 and R2, I need to find out UAB, UBD, UCD. So what I need to do is put. So next is the kinematics. So let me put first what? How did we do it? Put R1 equal to 1 and R2 equal to 0 and look at the displaced shape. When I do this, what happens? This comes 1, and so this, note that since they are hinged, okay, go like this. Now I need to find out elongation. How do I find out elongation? Well, I drop a vertical along this direction, and when I drop, I'll show this a little bit better because it gets a little bit complicated. So let me draw it properly. Otherwise, you'll have a problem. Okay, now since this point has come here and these points remain where they are, your new lengths are this. I need to find out what the increase in length is. Let me take BD, AD. Okay, it's given in this form where this is 3 and this is 4. Okay, this point has gone, I'm going to expand it by 1. So this is my new shape, and I need to find out the length. To find out the length, what do? I drop a 90 degree here, because remember, small displacements, if it goes perpendicular, then there is no change in length. Okay, so all I need to do is now find out, okay, if I dropped a perpendicular here, I need to find out how much this is, and this is going to be my UAD. So how would I find that out? Let's draw it. Okay, so if you look at this, okay, and I look at this and I say this makes an angle theta. Okay, this makes an angle theta where this is 90 degrees. Since this is 90 degrees, okay, since this is theta, okay, and okay, since this is theta and this angle is 90 minus theta, okay, what happens is that if you look at it, you will see that since this is 90 degrees, this angle becomes theta, and since this angle is theta, this angle is theta, and this angle is 90 minus theta. Okay, so if you look at the change in length, the change in length is given by R1, UAD is given as R1 into cosine of theta, because this is R1 equal to 1, so since this is 1, so it's cosine theta. Okay, UAD is cosine theta, and this way I can find out that whatever is the angle that it makes with the horizontal, okay, whatever is the angle that it makes with horizontal, the UI of that is given by cosine theta. In this particular case, it's going to be then that UAD is equal to, what is cosine of theta? You will see that this will be equal to 4 by 5, and that's positive 4 by 5. What about UBD? What is this theta? 90 degrees. What's cosine of theta? 0. Well, it makes sense, right? Because if it moves perpendicular to itself, the length of change of length is 0. And what about UCD? UCD is going to be equal to, look at it, it's going to be, if you look at it, it's going to be equal to the angle made with the angle is this. So it's going to be shortening, and that is minus 4 by 5. Okay, so that is, these are the displacements given in terms of cosine theta. Similarly, you will see that corresponding to R2, you will see from the kinematics. In other words, the kinematics for trusses is actually very simple. Okay, the trusses is very simple. It doesn't get very complicated. For trusses, you can actually write it down. In this particular case, this is my structure, and I give R2 equal to 1 and R1 equal to 0. Okay, if you put that, what happens? This will go this way, and the displacement pattern will be this and this. And all we need to do is find out how much of shortening that you have. The shortening or lengthening will depend on, again, perpendicular from this, and without, I leave that this thing up to you. You will see that UAD is going to be equal to R2 sine theta, where theta is this angle, and this happens to be minus because it is shortening. Okay, and same thing for all of them. In this particular case, you will see sine theta in this particular case is UAD will be equal to minus 3 by 5. Okay, and UBD, you will see now here when you do sine theta for the vertical member, sine 90 is 1. So therefore, you will see that UBD is equal to 1. And that is true because here, whatever the displacement is directly the shortening of the vertical member. And UCD is going to be equal to minus 3 by 5. So if we put this in, so we are done with the kinematics now. Okay, so if you plug this into the kinematics and into the equations, what do you get? You will get for AD my FAD becomes equal to EA by 5, and what do we have? 4 by 5 R1 minus 3 by 5 R2. Okay. All I have done is I have substituted UAD in terms of R1 and R2. I have got the influence coefficients for R1 and R2 from the kinematics, and that's all I do. Similarly, for BD, you have FBD equal to EA by 3, 0 R1 minus 1 R2, and CD is FCD is equal to EA by 5 into minus 4 by 5 R1 minus 3 by 5 R2. Okay, so these three expressions give me the forces in terms of forces in the members AD, BD and CD in terms of the displacements corresponding to the degrees of freedom. Okay, so once I have those, then what's the next step? Okay, see, I'm following exactly the same steps as I did for the flexure. The only thing that I have in this particular case is that I have, instead of flexural equations, the truss equations. Okay, so next step, well, next step, virtual work. And since I have 2 degrees of freedom, I have to write 2 independent equations. So my first equation, my virtual displacement pattern, R1 equal to 1, R2 equal to 0, and I find out the work done by external. What is the external work done? Let's look at what the force was. What were the forces? There was a horizontal force of 10 and a vertical downward forces of 10. So that external virtual work is going to be 10 into 1 plus 10 into 0, because R2 is equal to 0. So this is going to be equal to 10. Okay. So now, what about the internal virtual work? The internal virtual work is going to be FAD into UAD plus FBD into UBD plus FCD into UCD. Okay? And how are these related to R1? Well, I already have the influence coefficients. So this is going to give me FAD into plus 4 by 5 plus FBD into 0 plus FCD into minus 4 by 5. So if I look at it, what I get is the following. This equation gives me that I'm going to substitute FAD and FBD, CD in. So I'm going to get EA by 5, 4 by 5 R1 minus 3 by 5 R2 multiplied by 4 by 5 plus EA by 5 minus 4 by 5 minus 3 by 5 R2 into minus 4 by 5. So taking EA by 5 and 4 EA by 5, this will become 16 by 25, 64. So it's going to be 64 by 125 EA R1 minus, I'm sorry, it's going to be 16, not 64. 16 by 1, 4 into 4, 5 into 5 into 5. So it's 16 EA upon 125 R1 minus 12 EA upon 125 R2. Then plus minus minus becomes the same. So 16 EA upon 125 R1. And this one minus minus gets plus. So it becomes plus EA 125 R2 is equal to, which is equal to 10. This cancels this, so this becomes 32 upon 125 EA R1 is equal to 10. In this particular case, we actually get an uncoupling. Normally you wouldn't get our uncoupling. Okay, so R1 is equal to this, and the other equation is going to give me the virtual displacement pattern is R2 is equal to 1 and R1 is equal to 0 independent. In this particular case, the external work done is minus 10 into 1. So this is going to be minus 10. Internal virtual work is going to be equal to FAD multiplied by R2 is minus 3 by 5 plus FBD, AD, BD multiplied by minus 1 plus FCD multiplied by 3. Okay, so if you look at this one, we will see that the positive and the negative will cancel out, and what will be left with is 9 EA by 125 R2 plus EA by 3 plus EA by 3 R2 plus 9 EA by 125 R2 is equal to minus 10, and so this is going to give me R2. And what is R2 going to be equal to? Let us take stock of that. This is going to be equal to minus 10 multiplied by 375. So this is going to be 125 into 3, 375. So this is going to become 27 plus 27, 54. 54 plus 125. 125 plus 54 is equal to 179. So 179 EA. This is my R2. Now R2 is negative. Why? Well, because R2 is taken to be positive upwards. And so all that means is R1 is positive, it is to the right. It's positive, so it is to the right. Okay? And R2 is negative, which essentially means that R2 is downwards. Which is how it should be, because the way we have defined R1 and R2 is positive to the right, R1 is positive, and R2 is upwards positive. Obviously, under the loading, you will see that R2 will go down and R1 will go up. And therefore, what we have is, now how do we find out these values? Once I've got R1 and R2, well, all you need to do is, once you know R1 and R2, you can substitute into, and you can get FAD is equal to EA by 5 into, what is R1? R1 is equal to 4 by 5 into 1250 upon 32 EA minus 3 by 5 into, so this is minus, R2 is minus, so this becomes plus 10 into 375 upon 179 EA. Okay. So this EA cancels here. All you get 5, 250, 550, 8, 25 by 4. So this becomes 25 by 4 plus goes 2. Okay, so this is 6 into 375. So this is 1125 into 2 is 2250. 2250 upon 179. This is my FAD. And in exactly the same way, I can find out FBD and FCD. And once I know these, I know my member forces. And I have analyzed the structure. I have found out the displacements and I have found out the member forces. So you see, in trusses, it is relatively easier because the member force deformation relationship is simple. The kinematics is very simple. Okay, the kinematics essentially depends on sine theta, cosine theta. Okay, so kinematics is simple, and therefore actually the displacement method is very simple for trusses. The only thing is that for regular trusses, the number of degrees of freedom are so large that you cannot do a hand computation, and that's the reason why I have taken a simple example with actually loaded members to illustrate the concept. You will have to use computers to be able to solve for larger. However, the procedure still remains the same. Define the degrees of freedom, determine the number of degrees of freedom, define the degrees of freedom, define the member force deformation relationship, do the kinematics, do the virtual work, and then solve for displacements. incorporate the displacements and get the member forces. And that's all there is to the displacement method. Thank you very much. I hope at the end of this series of lectures, you are now comfortable with applying the force method and the displacement method for obtaining forces and displacements in both plane trusses and plane frames. Thank you very much. Bye.